Hey everyone, we're skipping the theme song for this set of lecture slides for 6611 to talk about assessing normality in a sample. We're going to introduce some graphical and formal statistical approaches to doing so that we can use in the future. So first, assessing normality. Why should we assess normality in the first place, especially if we finally made it to the good place? Well, oftentimes when we see some statistical tests, we'll note that there's an assumption that the data are normally distributed, either exactly or asymptotically so. If the assumption is violated, that test may not perform as we expect, and this could be in terms of having worse power than we might have imagined if we had perfectly normally distributed data. The results may be biased from what we expect, and so on. However, different statistical tests will have varying robustness to departures from normality. In other words, we do not always have to use alternative methods such as the non-parametric methods we'll discuss in a few weeks, depending on how non-normal the data is. One of the challenges, of course, is that it is somewhat context specific, and it does start to get into the statistics as more art than science because there's not necessarily a strictly right answer. However, it is good practice to assess normality and holistically do so by using both graphical and potentially statistical approaches. And we'll note graphical ones are oftentimes pretty good because our eye is pretty adept at catching a deviation from a pattern we might expect to see. Some things, though, to keep in mind as you evaluate samples, empirical sample distributions for normality. The first question we can sort of note as a question to triage if something's normal or not is, does the mean equal the median equal the mode? Now, this will be true for any symmetrical distribution, so it's not enough to just determine something is normal, but it could alert us to data that is decidedly not normal. Also, is the data skewed? We know that a normal distribution should have a skewness of 0, with values that are positive or negative indicating skewedness to the right or left respectively. And finally, what do the tails look like? That idea of kurtosis. The true normal distribution will have a kurtosis of 3, which is decidedly not helpful in looking at a figure, but we can sort of keep in our mind the shape of a bell curve and determine if the observed distribution generally reflects that. So for the rest of the lecture, we're going to simulate data from a normal and an exponential distribution, both with a mean of 10, so that x will be our random variable that's distributed with a mean of 10, mu equals 10, and sigma squared equals 1. And then our exponential random variable y will be exponential with lambda equals to 0.1. We see here we're setting our seed for reproducibility so we could reproduce these results. And we also see that we're going to simulate a sample of size 50 observations for each x and y. So let's dig into some of the graphical approaches and just do a brief overview of what they are and some things to look out for. One of the really great tools we have are histograms. So a histogram will group continuous data into some range, and you can play around with these manually, but are also oftentimes the functions will have some default approach to help you at least get an initial figure made. And it represents then the frequency of a range by the height of the bar. And in many cases, you can either specify, like we have here, the height to be the literal frequency, the number of times something fell within that bin, or you can also specify it as the probability, or the 10% of the time, let's say, this value was observed. So questions we can ask ourselves again, do we see symmetry, and do we see heavy or lighter tails? Now, of course, because it is a random sample, things aren't going to be perfectly normal for our normally distributed data. We can note if we were to try to draw a bell curve here, we have something that looks vaguely normal, at least normal enough that I might not be too worried. Whereas if I try to go over to our exponential distribution and draw a bell curve, I just not even really sure how I would do so without trying to just do something that's decidedly skewed. So this gives us a first glance at just looking at the histogram. If we didn't know the distributions they came from, for the exponential it appears somewhat non-normal, and we may be concerned depending on what we're trying to do, versus at left it seems to be somewhat normal because that is what we simulated from. Another really useful tool that I like a lot is the box plot. And it usually shows the first quartile, the median, and the third quartile in the box, where the first to the third quartile is also called the interquartile range. And then they have whiskers that will extend either to the minimum and the maximum observed value, or depending on how extreme the data is, if we have really large outliers, there may be some underlying calculation to determine the width or length of the whisker, and then put the extreme values as points. What we can see here is if it is a normally distributed data that's symmetric, we should have this nice pattern that we actually see in our normal distribution box plot, where we have the spread from the IQR, that lower to upper value, is pretty balanced on either side of the median. And again, the median then falls in between the two pretty equally. And then also the whiskers are pretty similarly sized just by eyeballing. This serves in sharp contrast to our exponential distribution, where it looks like our interquartile range may actually have some balance within that window specifically, but it's definitely skewed down to 0. We also then can note that there is a host of what we would consider extreme values, which further would maybe give us pause about the normality of the data, or if this was a real data set, we may want to dig a little deeper into what those values are and if they might be errors in the original files that we're using for the analysis, or if they're actually correct. Another great graphical tool is what we would call a normal probability plot, or a QQ plot. It shows the observed percentiles from your data versus some expected or theoretical percentiles, in our case, a normal distribution for these normal probability plots. Now, what we can also add is, with the QQ line function in R, a straight line, which would then perfectly match the points if we had perfect normality achieved, where deviations from the straight line may suggest there's a departure from normality. So what we can see by looking at the normal distribution's QQ plot at the left is that for the most part it fairly closely follows the line. We do see at either end there's some deviation from the distribution, but as a whole I would say I'm not super concerned with this data, which again stands in contrast to our dat-y exponential, where we see down below we have a pretty decent following of the line, and then it takes a sharp turn away from the line. All of these points here would definitely give me cause for concern, and maybe want to again dig into if the data is truly normal or if we need to do something about that. So that represents just a few graphical tests we can do, and a lot of them, once you sort of learn what you're looking for, can serve as a quick gut check to see if things are normal. Sometimes, however, people also request formal statistical tests. So the good news, there are a number of different tests out there that look for deviations from normality or even some other distribution. So examples of these include the Shapiro-Wilk test, the Anderson-Darling test, Cramer-von Mises, Lilliefors, Kolmogorov-Smirnov, etc. Attached to these tests, or most of these tests, is a probability that you would see a value of the test statistic, or one that is larger for the Anderson-Darling, Cramer-von Mises, Kolmogorov-Smirnov, or for the case of Shapiro-Wilk, a smaller test statistic if the data are truly actually normal, or in other words, the p-value of the test. However, a word of caution, it's best not to weight the results of these tests too heavily. If we have a small sample size, we may decide we have normally distributed data, even if the data was not normal and graphically we were concerned. And really large sample sizes can be overpowered to detect any moderate or even minor deviation from normality, so that graphically it may look pretty good, but the test formally says it's not normal. And that's sort of having to balance again the graphical and the formal testing and try to make a holistic approach. Here on the slide I provided just some R code for an example how we could calculate all 4 of these statistics at once to see what they all suggest. One of the challenges of doing this in practice is that if you have disagreement amongst the results, which tests you use, and unfortunately there is no good answer I can provide right now on how to handle that. But we'll see on the next slide the results for our simulated data sets. And so here we see the 4 different tests looking at normality, the function in R in the package it comes from, where we can note the Shapiro-Wilk test is a default function, and the other ones can be found in the NOR test package or in other places as well. And what we can see is that they're all testing the null hypothesis that the data is normally distributed. And that's what we're then looking at the p-value to see if we reject that null hypothesis. So again, if our h0 is our data is normal, we can look in our column for dat_x for that normally distributed simulated data here. And we see that in all cases, the p-value is significantly larger than the 0.05 threshold we commonly use. Therefore, we would conclude that we failed to reject that null hypothesis, and we would say our data seems to be normal. Again, this stands in a drastic contrast to our exponential distribution of dat_y. Here, every p-value is significantly less than 0.001, so it's so small, we're pretty confident that our data is not normal and we reject that null hypothesis. And so with that, we might say if it was that observed situation, we would want to look at alternative ways to maybe analyze the data that don't necessarily rely on assumptions of normality. So in conclusion, I will leave you here to read this quote by W.J. Uden, who people have made into a normally distributed word art.